Okay, hi everyone. Today we are very happy to have Alejandro Cabo-Bizet from Turin, who's going to tell us about why indices count the total number of black hole microstates at large n. Please.
Thank you very much, Minja, and thank you very much to the group for the invitation. It's a pleasure, actually. Okay, so this is the title of the talk. Okay, so but let me start with a brief introduction, and then I will go to the real content. No, so and these are trivial things that you all know, but it's just like a warm up to the main topic of the talk. Okay, so when to quantize the theory, essentially there are various ways of doing, but let's say the path-integral way of doing the Feynman way of doing it is you have an action, a classical action with some configuration variables g, let's say, and then you have a Planck scale which you add into the action and you associate the phase to a specific configuration in a functional space, let's say, and then one possible way of solving the path integral is in perturbations. No? Let's say in a semiclassical expansion, no, h bar going to 0 expansion is in perturbations around solutions, stationary points of the action S G. Now, these perturbations, these perturbative expansions around specific DC, specific solution of the equations of motion, are generically divergent. Okay, for generic theories, and but it is also complicated to find all solutions generically, all solutions to the equations of motion. No? So these are two different dimensions of difficulty, let's say. And in one sense, it's like if you fix one of these semi-classical solutions, then you may have actually missing non-perturbative corrections coming from the other semi-classical solutions, from the perturbation theory around the other semi-classical solutions. But then at each specific classical solution for each specific perturbation theory, you may also have infinities there. Now, generically, the action certainly may depend. It's a functional of the configuration variable G, but it may depend on extra couplings aside from the H bar coupling, from the H bar, the Planck constant. And generically, the dependence on these couplings makes finding or classifying all possible classical solutions very hard, very hard problem. In those cases, it is actually natural to consider to try to start the quantization procedure to consider a combined expansion where you go to a semi-classical limit, but then you also consider the small perturbations in the coupling simultaneously. And in that, of course, there is no a unique way of doing that if you have many solutions to a equation of motion, but there is a most natural one. One select, let's say, one of these semi-classical solutions, and which could be, for instance, the maximally symmetric solution or the least energetic solution. So it depends on the specific example, let's say. No? And then one starts. This makes the problem a little bit more concrete because it may be that G is the theory it's such highly nonlinear in whatever it is the perturbation that G is essentially measuring. But in the semi-classical limit in which you take G to be very small, generically the theory simplifies and you can find solutions easier to a equation of motion in that limit. However, that doesn't make the problem trivial at all. So it makes it a little bit more concrete for very complicated systems, but still not fully concrete in generic examples, no? Because essentially in the small H bar expansion, the semi-classical expansion, some of the coefficients in that expansion may be by definition infinity. No, and then you need to deal with the question of regularizing those infinities. And now those infinities may come from either infrared excitations around the specific background that you selected, or that your semi-classical expansion, this double expansion, is selecting, but they may come also from UV excitations around that specific background. And now the first instinct is to introduce a cutoff. For example, in the theory of gravity, say we can consider the coupling G to be the Newton constant. And in that case, if we select the background solution, semi-classical solution of the equation of motion, to be the least energetic one, the vacuum, what people call the vacuum solution, or could be one example in 44 or whatever, ADS 4, ADS 5. The natural UV cutoff is for UV divergences is the Planck mass, which is related to a Newton constant in this way for generic the space-time dimension in these units.
This is all for the Euclidean theory, presumably, right?
Well, I have not. Well, right. I have not said the Euclidean yet. I mean, I will discern. It's a bit vague thing, but this is not Euclidean. What I was saying, generally, in principle, you could also do it for in Lorentzian. No, it depends on the theory. How complicated is the theory you're contesting? At this point, this is very abstract. Then I will particularize to an Euclidean model. Okay, but at this level, yes.
Yeah. No, that's good. Yeah.
Okay, very good. Very good. Thanks for the question. Very good. By the way, if you have questions, please interrupt me. Do not hesitate to interrupt me at any time. Okay, very good. So let's see what it was. Right. Now, so if we select let's say the least energetic solution, the vacuum solution, somehow, whatever, the physics below the Planck, to describe physics below the physics involving energetic exchanges below the Planck mass, it is actually enough to work with in the presence of this cutoff, energy cutoff. So essentially, in the Wilsonian perspective. However, the problem is the following. What about if you are interested actually if you really want to understand fully quantum gravity, you really need to understand processes that go beyond the Planck scale of shell exchanges in principle. And to understand the physics there, the natural idea to try to make some progress is to instead of selecting a specific expansion that picks up the least energetic vacuum or the most symmetric vacuum, you may select a different expansion that selects a background geometry, a background configuration in a theory that is not gravity. There is not a gravity theory that probes in the gravity theory that probes those regions, very high energetic exchanges. And one possibility for that, of course, you need solutions. This need to be solution of the equation of motion. One possibility of this background is in general, are black holes. Is to pick up a black hole. Okay, but there are more possibilities. This is not unique. It's not the unique possibility. There are other kind of solutions which are very energetic. They do not need to be black holes. Okay. Now, what is significant of black holes is that they have an event horizon. And so if we go now to a Euclidean signature, and we periodize time, so we rotate the time and we periodize it with period beta, the inverse temperature, following Feynman prescription to try to say for statistical mechanics, statistical physics. Then the on-shell action of that gravitational solution at leading order in the semiclassical expansion that I was mentioning before, that picks it up, is to be interpreted as a thermodynamic free energy. Okay, and it receives, and this was found by Gibbons and Hawking for specific boundary conditions in genetic theories. It receives contributions only from boundary terms. For example, in the case of a black hole, from the special slice of the horizon. And so when one evaluates that for a black hole solution genetically, and then the on-shell action, and then one takes the Legendre transform of that with respect to beta in first temperature following Feynman prescription, that Legendre dual observable is supposed to be entropy. And that is what is called Bekenstein Hawking entropy of black holes that you know very, very well. All of you know very well. And this is the Bekenstein Hawking area law. So this magnitude S is interpreted as a thermodynamic entropy. And many people essentially contributed to this in the 70s and 80s, and this was later on generalized also when you have perturbations. One of the two kind of perturbations are, let's say, 1/g Newton perturbations, you know, in other cases, and even beyond that lately. But if one, so the summary so far for this kind of big introduction. So in the theory of quantum gravity, one really needs to understand the physics beyond the Planck scale. And black holes are overweight to that. So they are semiclassical backgrounds, so you could understand physics beyond the Planck scale, studying perturbations around that let's say, that specific backgrounds, classical solution of the equation of motion. Now, decidedly, a complete quantum gravity theory must control, of course, this is one specific perturbation, perturbative tail in the full quantum theory, theory of gravity, hypothetic quantum theory of gravity. So you will have many more kind of similar expansions around different background solutions, all solutions of the equation of motion. And in a quantum theory of gravity, in principle, that theory should be able actually to translate from different perturbation between different perturbation theories, between different perturbative expansions associated to different backward, to different, not backward, different solutions of the equation of motion. And they should also be able to control. One should be able to use that theory to control specific perturbative expansion, perturbative contributions around specific classical solution of the equations of motion. And this is the second point. Now, string theory provides various concrete setups where to address these questions. And in particular, for this talk, it will be relevant the gauge string duality. So it offers perspective on quantum gravity in which one essentially can try to address the questions that I mentioned before, but simply focusing on gauge theories, techniques, okay? And today I will focus on a specific example of this kind of dualities. The most famous one, ADS5 CFT, for kind of duality. And if one really want to have even more handle on technical outcomes, one may particularize to specific kind of gauge theories, which are supersymmetric gauge theories. And in that case, one simplifies a lot the analysis of the previous questions, the main questions that I mentioned before. But still, it's not that trivial, and we have not understood everything yet. I mean, we're far from yet claim full understanding of everything. No? But it's actually where the hope of really fully understanding what is a quantum gauge theory formulation of a quantum theory of gravity, not only at perturbative level, but also at the non-perturbative level, in the sense that I mentioned, may be achievable. So are there questions? Very good. So a natural question then using gauge theories is, can one use that gauge theoretic formulation of quantum gravity to reproduce black hole entropy? So using this philosophy that I was trying to outline before. So the best computational control is if one further specializes to supersymmetric black holes. Actually, not only supersymmetric gauge theories, super versions of superstrings in general, but theories. But if we specialize for black hole solutions, which are actually also supersymmetric. And to analyze those within using these gauge theoretic techniques, in the last 10 years, we have understood a lot about that, how to do that, also from the gravitational side. And there is sort of universal story that applies in asymptotically flat and asymptotically ADS, electrical charge and rotating black holes. And so the procedure actually to study them is the natural procedure is to start from families of solutions of the equation of motion, black holes which are not neither extremal nor supersymmetric, but that includes among them supersymmetric black holes. And the procedure then is so you start from this family, and there is one parameter there which corresponds to temperature of the black hole. So then, and there is another parameter which controls how far you are from the supersymmetric locus, from the supersymmetric solution. So the procedure is you essentially impose that second parameter that I mentioned. Essentially, you impose zero. Essentially, you restrict to the set of supersymmetric solutions, and generically that mathematically that is not equivalent to imposing zero temperature. But what happens is if you are actually working Lorentzian signature, is that generically those solutions which are supersymmetric, they will include naked closed time-like curves. If you do a weak rotation as these are rotating solutions, the geometry will be complex after you do that. And this specifically when you take the limit to supersymmetry, these solutions will have also complex entropy, whatever area of the horizon, but also complex charges naively, unless one goes to extremality. So in extremality, everything solves extremality and supersymmetry. Either in Lorentzian, there are no CTCs, and you are at the supersymmetric locus. In Euclidean, entropy becomes real, charges become real, and there is no problem with reality conditions, despite the metric being complex in Euclidean. Okay. So let me make a summary of these things, which are things that we have understood in the last 10 years. So if supersymmetry reduces the thermal, and this I will explain a little bit more in a while, but supersymmetry reduces the thermal path integral, the thermal of the semiclassical approximation to it, thinking in semiclassical terms, to a gravitational version of a Witten index. And then, but that's extremality, that's not enough actually. Then we need also to impose we don't need, but usually it is required to impose extremality, essentially to annihilate naked closed time-like curves. While doing that, as you are essentially imposing a constraint on the geometry, what you are doing at the level of charges is you are imposing a non-linear constraint between spin, the rotation of the black hole, and the electric charge of the black holes. And this nonlinear constraint is a little bit enigmatic, as I will explain in a while, for various reasons. Now, what is the goal of the talk? So first of all, why Witten indices work in a specific context that I mentioned before, despite not being precisely partition functions? I will explain. I will go over this. And second, what is the microscopic meaning, to propose a microscopic meaning of this nonlinear constraint that I mentioned before? So not from the supergravity side, but from the gauge theory perspective, the perspective of the states you are counting. No, the gauge theory you are using to count states. And as I said, so the tools will essentially move between these realms. So you start from gauge theories, they are supersymmetric. You can compute things using supersymmetric localization, and the path integrals reduce to matrix integrals. And that simplifies a lot the kind of questions that I was mentioning in the beginning. Now, why this could be useful? Well, to me, this is interesting, but why this could be interesting is because I do think that in the long term, these models are sufficiently simple to be able to actually study non-equilibrium gravitational processes, even though they may be relatively simpler with respect to more complicated theories of gravity, but still they capture something interesting. And even quantum transitions between different semiclassical solutions, even brain dynamics and all kind of related questions. Okay. So we are not yet at that stage, but I think we are relatively close. So then I will go into more technical stuff that was more like motivational preparation. So if there are questions, please. Very good. So So again, I will review the questions that I mentioned before in a more concrete way, and then I will, in a more intuitive way, propose an answer, which one should be able to follow, without knowing more details, many details. And then the thing will be to test this proposed answering in two independent ways, but within the context of UN four-dimensional n equal to 4 supergeometry theory, and with space S3. So it's the case theory on R times S3. And these two ways of doing it would be using saddle point approximation, which actually will apply at finite n, capital N as well, n equal to 2, but also at n very large, in infinity. And then at finite n at n equal to 2 in particular, this will allow us to do the integral we'll be able to solve by using just Cauchy theorem. And we will be able to test the predictions coming from the saddle point approximation in that example. Very good. So let me review the questions and then give this intuitive explanation of the answer before going into the main part of the talk. So again, the context is supersymmetric black holes. Schematically, it's Q is the supersymmetry associated that have a spin and electric charge. Generically, of course, you can construct at the level of supergravity boson in brackets at the boundary. And the spin generically doesn't commute with the supercharge, nor the electric charge. But then there is a single linear combination of them that do commute. Does commute with the supercharge. And that combination we call twisted spin, or math-frac J, as I'm mentioning here. Now, as I said, the nonlinear constraint that I mentioned before, it fixes a relation between the electric charge and the twisted spin or the spin. But I will highlight that the relation in this way for technical reasons. And so it is just that. So a relation between the twisted spin essentially generates, using that nonlinear constraint, generates specific value of electric charge. And in gravity, these are in a continuum that I should stress, okay? And what I said in words before is that so the area of the horizon is a function for the embedding set of solutions. So the supersymmetric solutions, which are not extremal, it depends on the twist spin and it depends on the electric charge. But it is only actually it is only in the region in which the electric charge is fixed to a nonlinear constraint value that I mentioned before, that we can actually reproduce the Bekenstein Hawking law starting from a Witten index generically. Now I'm talking generic theories, from a Witten index of some dual gauge theory by going to a semiclassical expansion that goes beyond the Planck scale, as I was saying, in the sense that large twisted spin expansion. Indeed. And so these are things that we know. But now, just to show this is a real plot, I will explain what is this plot towards the end of the talk, but this is a generic form that one obtains. So the black dots are essentially the values predicted by the Bekenstein Hawking area law restricted to a constraint locus. So this you move around the x-axis is the twisted spin, and the y-axis is the logarithm. So it's the entropy, Bekenstein Hawking entropy, and these are the black dots. But if you compute the microscopic models of indices, it's not that you really get, and these are the circle. This is one specific microscopic model, concrete one. The circles in here. It's not that you get actually exact match. People usually say that it's an exact match, but what you get actually is you get a lot of oscillations that are stationary. They do not go away. So you can go very, very high in the value of the twisted spin. The oscillations will remain there. They will not disappear. And so this is the Bekenstein Hawking area law, and this is really a microscopic result coming from indices.
Sorry, what are the two axes?
So this would be entropy, entropy and twisted spin, let's say charge, entropy versus charge. And the black dots are the predictions coming from the area law, the Bekenstein Hawking area law for entropy, Bekenstein Hawking entropy. And the circle dots, they are a microscopic computation using indices specifically. Okay. And generically, what you obtain is you obtain these oscillations, which do not disappear. It doesn't matter how far you go in the charge axis, in the x-axis, the oscillations will remain there.
So the oscillations grow like n squared?
Right, that's a good question. I will come back to this in a while. Yes, indeed, the frequency of oscillations is controlled by n squared. So it's actually becomes very oscillating if you are taking n very large as well.
But the deviation from the area law, does that also grow like n squared?
Yeah, indeed, because it's actually it becomes super oscillating. No? So it's only the top of this oscillating band. It's like a wave packet, and you have many oscillations, and then the area law is essentially on top of that of the wave. It's the top curve of the wave packet in that sense, in that analogy. So it's at some points the indices will go to zero, and the area law is actually going to infinity. That's what I'm saying. So that you cannot. Yes.
Why is it a puzzle? Why shouldn't the index not have counted the area, but the sign contributions?
Indeed, I agree. Yes, that's what I'm saying. No, but then that's precisely what I'm saying. Yes, no, I mean, it is a puzzle in the sense that the index is not solving really the full thing. No? So what I'm trying to explain why. I mean, what is the way of solving? I mean, this is not actually it's not wrong. The index is supposed to do that, as I will explain next. I'm just saying that there is another observable that actually it really gives the full neat area law without any oscillation.
So which is okay, good.
Very good. That's what I'm saying.
But all of the black holes here are BPS, right?
Yeah, I'm talking about only supersymmetric black holes, as I explained in the beginning. Yes, to have like analytic control over the thing.
Yeah, good.
Very good.
Good.
Very good. So good. So right. And the second thing, which might be unrelated, that I will address, is the meaning of this nonlinear constraint that I have been stressing. And the things, naively, you may say that these things are unrelated, but they are not unrelated at all. Actually, they are very related, one to each other. You will see. Oh, I will try to explain how. And now let me propose an answer before going into a more detailed thing. So the index, as somebody said there, so the index is actually defined in this way. So you're taking a trace with -1 to f in here. And this is not really a microcanonical entropy or a few supersymmetric state. That would be something like this. No, it would be a trace of 1, and then you're summing over states with charges J and Q. So the index I will define all over the talk as this D tilde, and the partition function, which the index depends on a single variable, which is the commuting charge with the supercharge that you select. And and the partition function depends on two variables, because you have twisted spin and electric charge. Okay. And the natural guess is that this is the thing that resolves that actually matches but we will see, because there is also this nonlinear constraint floating around. Now, the index is protected, actually. You can compute it at zero coupling, and that it's the same. It has the same value as infinity, as coupling equal infinity. But that is actually not the case of the partition function, of the BPS partition function. Because you may have states actually which are short at certain value of the coupling, for instance, 0. And then once you turn on this very small coupling, they may become a long multiplet, and essentially they do not. Right, and they are not. They receive also coupling corrections in there, and the index actually do not count those states, but this guy in principle does. Okay, So this guy is only piecewise constant in the coupling variable, in the gauge coupling variable for generic spheres, but it's not completely fully protected, it's piecewise protected. Okay. And so people do not try this usually because they go, this is no-go task. I mean, I cannot compute this from coupling, so it doesn't matter. Why should I care about this? Okay. And now, something that is relatively easy to see is that there is protected, even though this full thing is not protected, there is protected information in it. And that follows from the fact that you can express -1 to f, for instance, using spin statistic theorem in this way. But in specific theories, you can also express, for instance, I said that the twisted angular momentum is related to angular momentum by shifting in this the electric charge. So you can express it in this way as well, but you may express it in a different way, like this one. Okay, and that I'm putting these two examples here because that's what happens in the example of n equals to 4 for Jamils. So I will use this later on. And so we can use these two things, and then we can get some rules. So this guy is unprotected, but if you average Q in this way, you will get protected information. And this is exact here. And this thing is protected all over the coupling. So you can go. You can work with the free theory. This thing will be the same as strong coupling, and the same for the second line. So if you have various ways of representing the -1 to f which are independent, you will get independent sum rules in the theory. But again, this is giving a hint, but here there is an average over the electric charge. It's not really fixing a specific value of electric charge. Now, a naive guess is that the gravitational prediction for this constraint, this nonlinear constraint that fixes electric charges, charge as a function of the spin, which is non-discrete, okay? It's a sort of and it's a sort of coarse-grained gravitational charge. It's not really the discrete charge as in the fundamental theory. It's a sort of coarse-grained center of mass value for the sum rule. So something like but it's more like, I would say, like center of mass value. So in such a way that the left-hand side, in some thermodynamic expansion, selecting at large twisted spin, the left-hand side asymptotes, well, the right-hand side, or the left-hand side, one asymptote into a other. No? And that's a natural guess, okay? And so what this is saying, first of all, is if that center of mass value exists in some semiclassical expansion, like the one that I'm writing down here, then that would mean that actually in that specific region of charges, the trace with 1 is the protected quantity. And it is essentially equal, or asymptotically equal, asymptotes to an index up to a phase, up to an overall phase. Okay. And this is essentially what happens. I think this happens generically, but we will show this happens explicitly in n equal to 4 super Jamils. Indeed, and this is just a repetition of what I said. So, as I said, yes.
Let me try to understand. So
Yes.
So you say take large J, and for large J, but the index is still oscillating, right? For large J, or
Very good. Very good.
you want to say there is a way to extract from that
Indeed.
the actual
Indeed.
function.
Indeed. And it is this, not the index is oscillating, that right? But notice that this is oscillating and this is also oscillating. No? But really, but this thing is not oscillating. So if I take this to the left-hand side, this thing is, by definition, is non-oscillating. Okay. Very good. And notice, and let me take a very good question. So let me notice that there are various ways of representing, so it's independent ways of representing this. Okay. Very good. So that's very good. So any other question? Very good.
I mean, there's nothing special about gravity in principle, right? For this, could you not
say
have
that?
is there anything special about gravity for this? I mean, could I have taken quantum mechanics, supersymmetric
Yeah.
with a charge parameter.
Right. Right.
So-
Right.
Or
Indeed,
some
indeed.
quantum number. I can take large, right?
Yeah. I think if this really happens, at this point, this is I mean, it's not, this equation is true. These two rules are true. These are true actually in some theory in which you have enough charges for you, okay, and in which you can represent. I mean, you can use spin statistic and represent the -1 to f in these ways. So this is really general, no? And but now you need to prove this center of mass. I think that's the hard thing. You need to prove that really you can approximate this sum by using some center of mass value for this Q here, and that is what is a non-trivial thing. That is what I have not done so far. Okay. But yeah, this is universal so far. Yes, indeed. Very good. So this is, again, the summary of what I just said. So the trace with one inserted, it's expected to have, the proposal is that it's expected to have protected information at the specific dimension one locus of charges. Or said in a different way, as it is protected, we can even work with the free VPS partition function, the one that I said people usually discard as not very useful. We can work with that, okay? And even with that, we should be able to recover both the Witten index of two oscillations. I will explain what this means technically, but the oscillations that you have somebody else in the audience right now. And then you should be able to reproduce the Bekenstein Hawking area law without oscillations. Completely, exactly. Again, this is always restricted to a specific dimension one region shell. So that's the plan of the most technical part of the talk. I don't know how much time do I have, Minje?
You have about 25 minutes.
Very good. Right. So now the plan is to explain this in a specific, in n equal to post-Benjamin, as I mentioned before, how this happens. And as I mentioned, we'll do that in two ways. First, let's use a style point analysis. The context is this. I think, well, this is a trivial thing for you. You all know the thing. So it's UN n equals 4 to William Mills, apply a quantization, R times S3. And we will pick up from the conformal group specifically. So we focus on the isometry group of the S3. And the spin is actually a diagonal combination of two individual rotation, J1, J2. And Q is the diagonal combination of the three R charges. Commuting R charges, Cartan charges was before. So we will pick up two odd generators whose anticommutator gives this combination of even generators, which in radio quantization S is the dagger of Q. And so this magnitude here is a semi-positive definite. Usually it is expressed in terms of the physical spin and electric and our charge Q, which on the bulk correspond to electric charge. But today I'm expressing it here in terms of twisted charge and electric charge, twisted spin and electric charge. And this is what I said before from the gravitational perspective. So this combination, the twisted spin, is the one that commutes with both Q and S. And now for n equal to Young Mills and these selections in my conventions, both the twisted spin and the twisted R charge, and the R charge, and the R charge, they are quantized in units of 1/3. Okay. Very good. And that would be important in a way. Now, so to try to prove the thing that I mentioned in the beginning, so this center of mass value governs these sum rules, it is actually more convenient to work in grand canonical ensemble. So it fits chemical potentials instead of working in microcanonical ensemble. And then one can Laplace transform to a and so there, for instance, we start. So in n equal to first Benjamin Mills, again, free theory, we will test the thing that the universal argument gave before. So we start with the free theory. We can compute the partition function. It's going to be a huge expression that I didn't write here, but this is known. Okay. And you can get the BPS partition function. So the partition function counting only BPS states in the free theory. In the limit in which you take beta to specific limit in which you take beta to infinity. So the anticommutator of Q and S is precisely a BPS condition, and it's semi-positive definite when beta goes to plus infinity. then this only gets contribution from things that are related by Q and S, so which are supersymmetric. And this is the same D that I mentioned before. Before I was working for the sum rules, I was working in microcanonical ensemble, but now we are working in grand canonical ensemble. Okay.
So this is from the free field calculation or?
Free field calculation. The same thing that I said, that usually people discriminate this thing. It's just too simple. It doesn't work for anything. So that's all. That's enough to check what we said, no? Because the sum rules are protected. So if we are able to extract the sum rule from the grand canonical side, then that's even working with the free theory, we should get the right answer. Okay. Very good. Very good. So. And again, so the sum rules that I mentioned before are in microcanonical ensemble, but there is a version of that in grand canonical ensemble, and that version is just this thing here. So essentially, I can condense. This is the index that I defined before, the function of a single variable. Now we have the extra rapidities here, and I can define this shift test. So it's going to be a function of the chemical potential omega now in grand canonical ensemble. But then there will be these three possible shifts, either 0 or plus pi I or minus pi I. And these three shifts correspond essentially to the three options that I mentioned before. So if you take the BPS partition function, trace 1, we're now in grand canonical ensemble, and the rapidity alpha in here, I reduce to these three values. Let's say just semi-integral values. You can think of this. The simple way of saying this is just semi-integral values. And of course, there is mod 3 because the charges are quantized in units of 1/3 in here. Okay. So, but if you just alpha, you can reduce it to be in between minus 3/2 and 3/2. Let's say in between minus 3/2 and 3/2, there are three values of alphas that you can use to reduce the partition function in grand canonical ensemble to an index, and those will give the three choices of indices with the different shifts in the omega variable. Okay, these are just variants of the three of these three guys, of the three grand canonical variants of these three sum rules in microcanonical ensemble. It's just that. Let me come back. Good. But it's actually important now in grand canonical variables to recall this locus. So whenever alpha is restricted to half on integer, to semi-integer, then we are reducing the BPS partition function to an index. Just recall that's law. Again, the same thing that I said. So this is the locus. Whenever alpha reduces to a semi-integer number, the set BPS reduces to an index with shifts in the omega variables. The omega is the chemical potential dual to a twisted spin. Now, what's the observable that we will study? As we said, we really want to go to microcanonical ensemble, so we go to our DJQ again. And the way to go from grand canonical ensemble to microcanonical ensemble is to do its integral. As the charges are quantized in units of 1/3, we need these periods of 3. We need to integrate over a period of 3 alpha and a period of 6 pi I, the omegas. Okay? And that recovers the DJQ. So we need to solve this integral. To solve this at n infinity is impossible analytically by using Cauchy integral at n equal to 2. It can be solved by using Cauchy integral. We will do that in a while, very quickly. And but at n infinity, we can use, and the difficulty is in this set BPS, in computing this set BPS inside the integral. Okay. But so to work at n equal infinity, we need to use style point. There is no other way. At n equal to 2, we can use both things, style points and Cauchy integral.
Alejandro, I
Yes.
think your mic
Yes.
somehow didn't work.
Yeah,
Is
it,
yeah,
now it's working? Now it's
back.
working.
Yeah.
Very good. Very good. Okay. Please, very good. Thank you very much. I mean, so to go to microcanonical ensemble, we really need to integrate over this thrice period, usual periods, because of the 1/3 quantization. And we will do this in style point approximation and in Cauchy integral in Cauchy fashion at n equal to 2, but at n equal infinity only using style point. So these are the two semiclassical expansions that I mentioned. So n infinity at these large charges for the n square, but then we can also have n fixed, in particular n equal to 2, and large spin. We can also use that point approximation in there. And again, at zero coupling, This is the answer. In the paper, there are more details on how to deduce this thing. This is the matrix integral that one needs to solve. Again, the UIs are essentially Hermitian angles, so exponentials of 2 pi I UIs are eigenvalues of the unitary n times n holonomy matrix. And we really need to solve this integral. We want to solve it in saddle point approximation. Again, one can check using this expansion that you get the indices with the shifts that I mentioned before once you reduce alpha to semi-integers. Okay. And now how do we solve this? So we solve it so we're interested in size, so we can define an effective action in this way. So you take the integral and you take the logarithm of the integral. So as I mentioned, the integration variables U and J's are these. These are the capital U and J's that I will use next. And we are interested in studying the asymptotic behavior of this integral near its worst singularities, which are essential singularities. And these are actually localized around, these are essentially located at when omega is 2 pi I some integral. So you will take that expansion, so we will explain next, and then we organize that expansion in this way. Here, for B effective Mn is just the coefficient of this guy, and it is a function of the variable u. And then we find saddle points of the full guy, okay? Knowing the Taylor coefficients. Okay. So how do we find those Taylor coefficients form factors? We use this identity here, well-known identity for the Bookhammer symbol. And but instead of summing, for technical reasons that will become clear in a while, we will cut off the sum from n1 to infinity with some cut off lambda. Now, and P and Q, we will take P is equal to Q. Remember, in the integral, P and Q are equal, and they are the exponential of the chemical potential omega.
Your microphone is again off.
Again off. I think I will then let me just.
We cannot hear you.
Yes, let me.
That's interesting.
Still no sound. Oh, yeah. No, not yet.
Lifting, some reason.
Wait a second. Let me stop sharing the media.
Oh,
You're back.
yeah, you're back.
Just a second. I think there is some issue with that. Can you hear me? Can you hear me now?
Yeah, we can hear you.
Okay, then let me just remove the mic. And let me share it. Okay. Okay, so you can see now well, very good. Okay. So, oops, yeah, okay. So now the thing is P is equal to Q is equal to E to omega. Okay. So remember we are cutting off the sum over n. And now to recover the final result, we really need to take the cutoff effective Taylor coefficients and take the limit lambda to infinity. Okay. Now the cutoff effective potentials at different values of m and n, notice that they take this form. Schematically, don't look into details. It's just essentially polylogs, combinations of polylogs. Okay, and you can go arbitrarily high. Okay. And notice that there are always combinations of this. And there is always x, y, and z inside. But there is always this guy that doesn't have any prefactor in here. I will come back to this. And x, y, and z, they are simply this thing here. Okay, there is some combination, linear combination of alpha. That's already reminiscent of something. Okay. Oops. Good. Now, at any value of m and n, one can solve for saddle points. Actually, the solution is very simple. If you use capital Uij equal to 1, it's a saddle point of the cutoff effective potential at any m and n. Okay. And if we assume the delta omega smaller than 0, which is just a convergence region, the usual convergence regions for the Q series expansion in the integral, when you expand the integral in some way, you actually notice that when you evaluate the on-shell action, so the potential on the saddle point with some I epsilon prescription, you actually get, and take the exponential, you actually get 0. If this linear combination of alpha, 1/2, and n is labeling the specific essential singularity we are probing, is different
from plus minus 1. Now this, after some work, we can actually see that this is precisely the loci that reduce the BPS partition function to superconformal indices. And so what this is saying is that all these saddle points, and these are actually all the saddle points at finite cutoff lambda, okay, that you can find at finite cutoff lambda. What this is saying is that in that cutoff problem, all saddle points of the BPS partition function of the approximation to the partition function, no, doesn't matter how large is lambda, are also saddle points of the index. And indeed, implicitly, indeed, that's what I said. And that means that in near that those essential singularities, the BPS partition function is reducing to an ensemble of superconformal indices. I will write down the expression in a while. Now let me be a little bit, let me explain how this happens. I mean, how this zero comes up. Just a technical reminder. So if you take polylobes with negative order, you can always spread them in terms of geometric series by applying LF time, the logarithmic derivative with respect to u. So if you are using this series expansion, you necessarily need to have absolute value of the argument u smaller or equal than 1, and u needs to be strictly different from 1. In here, I'm taking lambda equal infinity. Okay. Now, this is a technical fact. So this diverges when u is equal to 1, obviously from this equation. Okay. And you cannot use it away from the units, outside the unit circle. Now, if you remember the things that I show in the list for the cutoff effective potential, they were always coming in these kind of combinations. I took one of the specific combinations. So let's focus on polylogs with negative order. So m plus n larger than or equal than 4. Okay. And there is always this minus 1 to this power, a specific power in the linear combination. Now, for the reason that I explained before, if I take lambda to infinity, first of all, if I want to make sense of these two series, and lambda going to infinity, necessarily I need the both uij to have absolute value 1. This is okay because this is the contour of integration I was using in the beginning. Okay, but then you also need yes. Was there a question?
No, there was.
No, very good. So, right. So, but for the technical reason that I mentioned before, this guy, this second guy, he has a singularity always at uij is equal to 1. And if set is different from 1, that singularity cannot cancel with this one. Now, what happens is that unless set is equal to 1, these singularities will not cancel. And if set is equal to 1, these singularities with this precise prefactor will cancel among each other, both of them. And you get a finite answer precisely. Now, if set is not equal to 1, if there is no disbalancing between these two terms, then you will get infinity as an answer. But if you in the region of delta omega that I mentioned before, that infinity you get is such that the exponential that you get, it actually goes to 0. And this is what I mentioned before. This is this identity here. Are there questions? Very good. I know this was a little bit fast, but okay. So anyways, so unless set is equal to 1, you essentially will not get non-trivial answer from the saddle point to the full path integral. And there are more combinations of saddle points. From those other combinations, you get other constraints of that form. And those constraints give precisely the loci that reduce the BPS partition function to indices. So when we combine everything, what we get is a formula of this form. When we expand set BPS, the BPS partition function in grand canonical ensemble, in specific vicinity labeled by this integer number n, we get this formula here, plus other corrections coming from other vicinities. Okay. And notice that there is a sum of, this is a periodic delta function. The prefactor doesn't depend on L, and this is a different prefactor. There are these two prefactors in here. There are two different families. Plus minus, the difference is in here. This periodic delta function has an important physical consequence that I will come back to explain next. There may be other style solutions. In the paper, you can find the details. They always require this balancing condition, which reduces the BPS partition function to an index. Otherwise, you get zero contribution in that semiclassical expansion near essential singularities. Okay. So there are what I call eigenvalue instanton saddles. There are also other things that in the paper are called dressed or before saddles. The physical interpretation of these ones remains unclear to understand. They are also saddle points of the index. That's an important thing to say. And then there are also other rational singularities that we can find the answer of two things. The gravitational interpretation of that has been understood. Okay, these are all before solutions in the bulk. Very good. So let me come back then to the problem. I mentioned this technical side, but let me come back then to the original question. So we have the microcanonical index, we have the set BPS in grand canonical ensemble. We need to solve for this Laplace transform in a thermodynamic expansion in which J is large, much larger than the unit of quantization, which is 1/3 in this case. Now, in these delta functions that I mentioned before, there are actually 9 of pair complex conjugated contributions selected. We can focus on the orbifors m equal to 1 singularities. Those will lead the counting of states, the asymptotic expansion of the JQ of the full partition function, free partition function. So they come in complex conjugate pairs. In particular, there is specific pair which takes this, the two contributions take this form, where S plus minus are just the extrema value of this guy. So you need to extremize with respect to omega, this functional here. And this functional, this extremization, we have a real part, S, which will match the area of the horizon divided by 4 Gn. And then it will have also an imaginary part that depends both on the twisted angular momentum. Now, whenever two of these saddles dominate the integral, this integral here, there are sign oscillations, and the sign oscillations are simply the sum of this guy here and this extra phasing here. So it's proportional to this combination here. So that means that it is only, sign oscillations only disappear in this codimension 1 locus. So when the charge Q equals the value predicted by the nonlinear constraint, precisely from gravity, because this is the same entropy function that you need to extremize in gravity. Okay. Thus, the positivity condition of this object here, which is the integral we are computing, implies that these saddles can only dominate the Laplace transform in the codimension 1 locus predicted by the gravitational side of the duality. In the leading asymptotic behavior, in the semiclassical expansion that I mentioned before at large spin. So, this formula here. And by definition, this because the entropy function is the same as the on-shell action of the dual black holes, this thing is just the area of the black hole horizon divided by 4. So to match with gravity, and this is what I said before, just in formulas, written in formulas, we just need to identify the Newton constant with the rank of the gauge group in this way. And because of the reason that I explained before, you actually get the result on the nose. Even at n equal to 2, actually, no? Which is curious in the large spin expansion. So a quick summary before moving on to the last part, very quickly, is that the natural observable to count BPS states is really, and it can be done at least in the codimension 1 region of charges, is really a BPS partition function. And in the codimension 1 region of charges that gravity gives as an input or whatever, it comes as well dynamically from the gauge theory analysis that I just said. This equality holds approximately up to the oscillations, because in the index you will have the combinations of these two guys, and they will not cancel. I mean, the imaginary part will not be canceled in there. Okay. So that's what I mean by averaging out oscillations. The right-hand side has oscillations, the left-hand side doesn't. Okay. And let me just make a couple of interesting comments before moving on to the last part, the last slides. So we have shown actually that the zero coupling computation works. So we started from the BPS partition function at zero coupling, and we reproduce the area law starting from there. But something very interesting is that the answer we have obtained, there is this periodic delta functions coming in. If you use, remember in gravity and in saddle point approximation, the charges are continuous, no? Because you are in a coarse grain description. So there is always a question on how do you go from the continuum to discrete? And this periodic delta function thing, which is a quantum thing, is actually doing that work. So if you use Poisson resummation, you can write it down as a linear combination of the phases, which precisely is telling you that the charges are quantized in units of 1/3 on the nose. So the sum over L's, which are essentially going over different indices in the ensembles that enter into a formula that I mentioned, that I showed before for set BPS as a linear combination of many indices, this is what one gets. So let me go to the last part. Are there questions? Very good. So at n equal to 2. At n equal to 2, again, we come back to the same integral. Now we can actually solve this in a Taylor expanding in these two variables here. This is a rapidity in small variables, small rapidity, which is e to the omega. And then you can define a second rapidity, which is a combination. This is essentially the rapidity dual to an electric charge at fixed physical angular momentum, not really twisted angular momentum. So we expand in small q and small t, the integrand of this, and we compute the integral value. And this is the answer that you get for the coefficients of t to the 4/3. So this is the R charge equal 4/3 counting of operators at different values of physical spin that you get in the free theory. Okay, these are the numbers that I will use. Now, before plotting these numbers, let me show the answer in this case for the index, which are these oscillating points that I mentioned in the beginning. This is the plot produced from that. This log d tilde. And this is the answer coming from the SJ, which is the real part of the extremization problem that I mentioned. The extremization of the functional that I mentioned before. So those are the black dots. And you see the oscillations of the index here that do not disappear. And this is the area law of Hawking as a function of twisted chemical potential. Some linear combination of that. Now, the integrals that I showed before are this circle, these circles that I plot here. This is still the saddle point approximation, the area law. Okay, but this is now the microscopic computation of djq at n equal to 2 in the free theory. So this is the plot of the djq. So log djq. So log djq, but a charge q, R charge equal 4/3. Sorry. Okay, and right, and notice that it didn't need to be the case, but it intersects at some point, no? And then you may ask the question: is this intersection precisely the value that gives the nonlinear constraint or not? So as we said, the djq is really a function of two variables, but it only matches the index if you relate q and j. Okay. And indeed, that's what I find. That's what is plotted in here. Okay. This is this triple intersection that I was mentioning here, that I plotted here. Okay. So indeed, the horizontal dashed line is just one. The circle dots are the physical, are the microscopic computation, and then the vertical line is the value of j, the value of the physical spin, that is fixed by the nonlinear constraint starting when you fix electric charge to be 4, okay? And that is approximately to 21.9574. So you plot this, but this vertical line could have been in here, for instance, or could have been in here, or whatever, in any other place. But it happens actually to be almost there. And this is not Q infinity yet, okay? Almost there at precisely where the quotient between, sorry, I didn't say this. What I'm plotting here is the quotient between the area law and the microscopic computation. So when the area law and the microscopic computation become 1, they become equal, that's precisely the value of spin predicted by the nonlinear constraint when the charge, when the charge is equal to 4/3. That didn't need to be the case, and it is indeed the case here in this microscopic computation. So this is actually confirming our results at n equal to 2. So this keeps repeating. I checked this for different values of electric charge, of R charge, and it's always the same thing. But of course, computing those numbers becomes very, very hard at some point. And I can only reach with the current computational power that I have with a laptop, essentially. I could only compute this up to Q 4/3, okay? Without waiting for weeks or something like that. Maybe more in that case. So this confirms.
Alejandro,
Yes, please.
time's almost up. If you
Very
could, finish
Yes,
reading
yes.
like a few minutes, that would be great.
Very
Thanks.
good. I'm finished. Yeah, indeed. Thank you very much, Minja. So this is just the same plot extended to higher values. And again, this happens for different values of charges. So the conclusion is the following. The free BPS partition function recovers both the Witten index, averaging out oscillations, as I explained before, and it recovers also Bekenstein Hawking area law. When restricted to the codimension 1 region of charges, which is precisely a one dictated by the gravitational solution or the saddle point analysis, as you wish from the gauge theory perspective. And so let me just make final comments before finishing. So in the paper, we also show that, as I mentioned before, ZBPS is piecewise constant function, is a piecewise constant function of the gauge coupling. We are currently studying how to study the potential discontinuities, how to quantize, how to study exactly, how to classify those discontinuities in a precise way, okay, and describe them in a precise way. It is missing a gravitational interpretation for other cells that we found in the paper, things that we call eigenvalue instantons dressed or before cells. Maybe relatedly to this, there is a question on whether the area of the horizon in Lorentzian signature, which is still real, outside when there are naked closed time-like curves, is there also thermodynamic entropy? Is that also entropy or not? In other words, is that related also to, is that area of the horizon reproduced by some of these other cells that we have found or not? That's related to some conjectures by a group, by a work from Chiraz Mingwala and Seo Kim and collaborators that we are trying to understand. Okay, there are some conjectures in a recent paper by them, which may be related to the things. And so the final message is that the BPS partition function is really the natural observable to study finite n questions. And if you do not want to go to large spins, then you really need to deal with these discontinuities that I was mentioning in the first point. But in the large angular momentum approximation, that's not necessary. It is enough to work with the free theory answer. Of course, there will be questions like, for instance, are there giant brain expansion for these observables? What are they? How do you describe those relations in a better way? Relations, what is this predicting for the analysis for truity or not? There are many there are other interesting questions that may be asked, but I will close here. Thank you very much for your attention. And my apologies for the interruptions.
Are there further questions? It's not.
It's really intriguing that you can extract
Mhm.
ZPPS directly from a localization computation. Yeah, even in this limit, even in some specific limit, it's surprising. So somehow you're saying like the index. I mean, somehow you're saying free field theory is enough. For
To
ZP.
extract the area law. Right. So it's I think it's just this. So it's this really happens,
Yeah,
right? And that there is a sort of center mass value. And that's what I showed using saddle points and then explicit computation. No? So there is really some intersection. There need to be an intersection in this microscopic side, no? But by using explicit Cauchy integration. So this didn't need to be a case, no?
yeah.
But it's actually, well, this thing here. So the saddle point approximation. So it's always this case. So this is the microscopic approximation, and this is the saddle point approximation for the index. Okay. And there is always an intersection here. Okay. And that intersection happens precisely at the value predicted by the nonlinear constraint. No? So that confirms this intuitive answer that I gave before. No? So it's really like center of mass average of this sum in here. So I agree. I did not. I mean, well, it needed to be something. Well, it could have been even much larger. No, the natural expectation is that if you are on the free theory, you are overcounting, no, the number of BBS states. So you should get much larger than that, than the area of the horizon thing. No? But it's actually giving. It's no precisely at that constraint is giving the right answer. No? And that is yes.
Could you have done this with how little Susie could you have done this with? N equal 2 would have been enough, or
I think in superconformal, well, one is to write. It's harder to write. You need to write the index for other superconformal theories. Well, that's for the free theories is there, and so in the paper is there, no? The prescription to write down. It's just the building blocks are there to write down the matrix integral, the analogs of this, and the analogs of this for the different superconformal theories n equal to 2. Okay, but it can be done, right. It can be done. So I think this balancing condition is a universal thing. I mean, this is the non-trivial thing. No? So at large enough values of m and n, this thing evaluated on the saddle point essentially goes to 0, unless you saturate this equality. Okay? And that's precisely this localization formula here. Indeed. Which actually is also telling you how to recover the discrete spectrum from the continuum in there by using this Poisson resummation thing that I mentioned before. By using this thing. No? Now, there are many essential singularities. And so you may ask the question, what happens if you essentially are not asking leading asymptotics, but you want to get more precise answers? That's much more complicated. I cannot say more about that. But yeah, I think it is right. Right, that's what I said. Thank you very much. Okay.
Any further questions? If not, let's thank the speaker again.
Thank you very much.
Yeah, thank you very much.
Thank you. Very, very interesting.
Thank you very much for the questions and for the invitation as well. So, and I apologize for this. I mean, at some point there was some interruption. So, but it's a little bit late.